Okay, so we can start today's class. Well, today's we will first finish our chapter 2 and then go to the chapter 3. So we will have a quick review about the content we mentioned last week. So last week we just stopped here. We also mentioned some property about least square where we treat it as a projection. So we just build the connection between the projections of feature space and also about our target data. Well, so we will have a quick review about our model. So here I would like to point out some kind of things. So we may not just quite clear state. So last week we have just mentioned, so we focus on linear model. So the model we given, so is written down at this part. So it's y equal to z times beta star plus the epsilon. So here the y and z just stand for how here is just this is just such kind of assumption. So where we assume how so our observation data is like the zi and yi. Maybe zi and yi. We have the 10 n data in total. And to handle this problem, so we propose a linear model. And the linear model is just an assumption. So where we just assume that zi and yi have some kind of relation. So where we assume that our yi, maybe write as small yi, is like zi beta star, adding the epsilon I. So I from 1 to n. So we have some other assumption on the epsilon I, okay? So but first we just you probably we have just mentioned, so what is the assumption on the epsilon I? So it's not only this kind of linear form, also have some relation assumption on the epsilon I, such as the independence and also the mean and the variance. And so this is our assumption. And now we just based on this assumption, trying to recover the value of the beta star. Recover the value of beta star. So we have the data, and this is our assumption. So which we assume that our data is come from here. So it's come from a linear combination zi with some beta star, but we don't know what is that, and also with additional, also with some kind of the noise just presented in our yi. Well, so this we have just mentioned at the beginning of the chapter 2. So this is the way. So originally, like the regression problem, we want to find the zi equal to some f. We want to make yi equal to some fzi, and our linear model just specify. So what is the f? So it's specified as this linear model, and then we no longer need to find what is the f. So our problem is degenerated to find what is the beta star. Okay, so the least square estimate is a very special estimate which want to recover the value of the beta star. So our least square estimate is just one special estimate. So just one special estimate. And one straightforward question is like, so what is the relation between the beta hat and our beta star? What is the relation among them? So our property 2 is told us, so what is the relation between the beta hat and beta star? So the important thing is that, so we already suppose that we already know. So this is our least square estimate. And our model assumption assume the epsilon is some random variable. So which means this epsilon have some randomness. So therefore, each our observation yi is also have some randomness. And eventually, so if we combine, we do some kind of calculation among the y. So the beta hat is also some randomness. So the beta hat is some random variable, and we want to know what is the relation between this random variable and this beta star. Beta star just stand for some certain unknown mechanism about our data. Okay, so beta star is already, it exists, but we don't know the value. So it's just some constant, some vector, some usual vector. But the beta hat is just some things we just have the randomness. Our first property is trying to see the beta hat. So is also a normal random variable. So with the mean beta star with the variance presented here. So it's actually we call it as a covariance matrix. We will have a quick review about what is this kind of the statement, what is the mean of this type of statement. Okay. And you may just think, so what is this assumption stand for? Okay, what is this assumption stand for? Assume that epsilon just belongs to this normal with a mean zero and with a covariance sigma square times the identity matrix. Okay, so here sometimes so you should be keep in mind. So the z is just our earlier matrix. So it's a r it's n times r plus 1 matrix. So therefore, the presented form here is also a matrix, and this is a vector. So what does this thing stand for? Okay, so we will have a quick review about the randomness. So we have mentioned that, so randomness is always just use a random variable to describe the randomness. So it stands for, so the random variable just stands for it may have the several possible outcome. And we also need to, so to describe its randomness, so we use a probability to describe. So we use like in this special example, so we use a probability mass function to describe, to measure the randomness. So just to have this kind of style. So they can take two value and each takes a 0.5. And the things we will talk about is a normal distribution. It's just a very special kind of random variable. It's a very special random variable. And it's also called as a continuous random variable. So where we use such kind of the function to describe this random variable. So this function is trying to describe, so this variable can take several values. So for randomness, we just needed to describe, so what is the probability? So this random variable can take in the certain value. So this is the random variable stand for, so have the two things, so which kind of value they can take and what is the corresponding probability, and that will become constitute our random variable. So the normal distribution is a very special random variable. And we just use this type of curve to describe the probability. So here we just consider we have a x, so which is our normal distribution. And how the function describes the probability. So if we use this function as a fx, so the probability that we're trying to describe so this is a random variable, okay? So it can take in different value and also with certain probability. So how we use this function to describe the value of x, the probability of x. So here we just use this type of thing. So where we're taking the integration over the fx dx. So just suppose our integration region is from a to b, and then this one just corresponding to the probability that are random variable, so between a and b. So this function, so therefore, because these things hold for any arbitrary a and b, so it's just describe, so what is the probability x belongs to some certain region. So that just matches our purpose. So it just told us, so what is the probability of x? So given some certain region of the x, we can just answer, so what is the probability that x in this interval? Okay, so this is what kind of this function play a role here. So and if we know the integration part, so we know this integration from a to b just stand for the area under the curve. So which means if we consider the two line, just suppose this line just corresponding to the a, and this line corresponding to, so this corresponding to x equal to a. So this corresponding equal to x to b. So therefore, the integration just stand for the area of this part. So the area under curve. So this, we're taking the integration. So the area is just this part. So this is what is the value we can find from integration. So naively speaking, so this function just play a role. So after just whose area under this curve, it's just corresponding to a probability. Okay. So some usual things that how we use a probability density function to describe the probability. Okay. And normal distribution is very special. It's just the special just come from this fx is have a explicit form. So this fx is written down as this form. So it's written down. So the formal fx we have seen is just depends on. So we see that z is follows a normal distribution with a two parameter mu and sigma square, and whose probability density function we have seen fx before. So it's just equal to this type of value. So one is 1 over square root of 2 pi sigma square. Another is an exponent with a power of negative x minus mu square divided by 2 sigma square. So even though it's a complicated form, but this guys is pretty useful. So we will see later, okay? But the key things is that we know the normal distribution is actually a family of the distribution. And the family just depends on the value of the mu and sigma. So for different mu and sigma, we will have the different corresponding fx. Okay, so it's very easy to see that sigma play a role at this side, and the mu play a role so at this part. So different mu and sigma definitely create into the different fx. And this mu and sigma is very special, just corresponding to the expectation and the variance of the random variable. So expectation of the random variable, so if you forget, so it's just standing for what is the average value of this random variable could take. So we just write down the explicit form. So it's corresponding to the integration between the x times the fx. So it's an integration of x times fx. So from the integration over the whole part. So just because this x just stands for the value it can take, and fx is corresponding probability. So so you just consider all the possible value x can take, and just taking the weighted average with the probability they can take, and then it's just making a rule at the average value this x can take. Okay, so the value times the weighted probability. And the variance is also special. So it's commonly write down as an expectation of x minus ex square. So it's x minus its expectation and taking the square and also take a further expectation. So usually, so one thing we should first come to mind is that, so x is a for any random variable x. So here we use a z, but yeah, just stand for the another general random variable. So for x, so it's stand for a random variable. But after we're taking the expectation, so it's a constant. It's a constant. So because so even though it can take in different value, but once we're taking the average, so they are just become a constant. So we don't have randomness anymore. And therefore, so this just stand for we're taking the expectation minus x minus ex. So commonly, I will just write down as this form. So it's also the x minus the expectation part fx dx. Okay, so it's just writing down as this form. So if you probably have used a random, if you have used a kind of the no use the started the probability before, so you can definitely get what I mentioned here. So if you know, you can ask me after the break, okay? So it's just common important things. So normal distribution we will meet very often. And well, so this is what it stands for. So the normal distribution is very special. So once you know the normal distribution, you know it's a normal distribution. The next thing you should figure out is what is the mu and what is the sigma square. So then you can identify the corresponding probability density function. Well, so how to identify mu and sigma? You just find the expectation and find the variance. Well, this one we have mentioned earlier, just we assume that our noise is a normal distribution, okay? So where mean is 0 and the variance is a sigma square. So just corresponding to the case where we're taking the mu as a 0. So just the x square over the 2 sigma square here. Well, so this is for the one type of normal distribution. So the normal distribution. And we also have the, so here I left some reference for you, just told you how the mu and the sigma just play a role. So when we just for our earlier function, okay. So maybe we just take the one as an example. So the mu here corresponding to our curve is just corresponding to where is the peak of this curve, the peak of this curve. So here it stands for the peak part. So here we just have the two normal distribution with a different sigma, but with the same mu. So curve one just stands for the mu one. So with the light blue color, and the curve 2 just with the color so brown, so it stands for the one that has the smaller sigma. So curve 1 has the large sigma and curve 2 has the smaller sigma. The sigma just play a role which stands for the variation. So the variance, commonly we state the sigma as a we state the sigma is just trying to describe how far the x, what is the distance between the x and the expectation of x. So for a large variance, just corresponding to x is far from its expectation. So in most of the case, and for a small variance, it's just corresponding to x is close to ex. Okay, so this is a variance sometimes we just call it as a measure of the fluctuation, or dispersion. So we're trying to see what is the distance between a random variable and its expectation. So therefore, so the curve 1 have a large variance just because we can find sometimes this x. So this just stands for, so the so the area under curve just corresponding to probability. So we can find x can have more probability compared with the brown one have the more probability to taking the extreme value. So the tail part. So like this part. So you can find the blue curve will have the more area under the curve compared with the brown one. And here is also. So therefore it can take more value, take the value far from the peak with more probability. So that stands for they have the large variance. So large sigma one. So just some kind of intuitive about how we, some illustration about how we understand the mu and sigma. Any question? Well, so we have just so this is just what is the mu and sigma for the same mu with different sigma. Also have another curve for you, but I will not go to the detail. Just how the mu play a role. So it's mu just also changes the peak, and also how the mu and sigma play a role simultaneously. And this is for the we sometimes call it as a univariate normal distribution, where our x can only take x is just can take in some certain value, some real value, but sometimes just like our earlier statement. So we just state what is the distribution of beta hat. Beta hat is a vector. So now we're just wondering, so what is the distribution of the vector, a random vector? So the earlier thing we called as a univariate normal distribution. So with this probability function. So a straightforward way is that we will change this sigma square to something we call it as a covariance matrix. But before that, let's just think about, so what we should do if we want to describe a random vector. So for example, I have a x1 and a x2. So if we want to describe as a normal, okay. So first of all, there are several things we need to consider. So of course, like the mean expectation of this term, and so expectation of x1 and expectation of x2. So we need to know the single information because we know there are some random variable. We want to describe what is the probability they can take. So they can take any, maybe they can take any value. So like any value a and b. So which is belongs to the 2-dimension. So therefore, we also, when we just describe the probability, there are some which kind of thing we need to consider. So we need to consider a very special key information compared with the univariate case is that we need to think about, so how the relation between the x1 and x2. So what is the relation between x1 and x2? So I just point out a very special example. So is that, so if our x1 is just equal to negative x2 just equal to negative x1, actually there have this kind of the random vector is very similar like the x1 because we just know the x2 is a negative x1. So therefore, when we're trying to describe the probability, we will of two vector, we also need to understand what is the relation. So we cannot just treat it x1 and x2 separately. So we should also just consider what is the relation among them. So therefore, it will directly generate something we call it as a covariance matrix. So the covariance matrix is defined So it's defined as which kind of the covariance matrix just defined. So just like it's a standard generalization of the variance. So it's just a describe. It's a matrix. So it's a variance x1 and a variance x2. So at its diagonal part, and also have the covariance part, x1 and x2. Covariance part x1 and x2. So these two things presented here is trying to describe what is the relation between x1 and x2. So the variance of x1 we have no, just like in the univariate case, it stands for the sigma square in the normal and also some other sigma square here. But we also include a covariance part. Include a covariance part. So if you have interest about this covariance, so we will take more kind of the kind of content. So I just skip here, okay? So but if you have interest, you can just take a look about the definition. So you should also describe. So what is a joint? So you should describe so it just depends on both x1 and x2 to compute this covariance part, okay? So if you have interest, you can just take some reference book to, but we will not, in our course, we will not directly to compute, okay? Just need to know. So why it's a matrix and what is the value presented here. Now, so therefore, for a multi-dimensional case, and also like the Gaussian, especially for the Gaussian random variable or the normal distribution, so that just stands for same, okay? Gaussian distribution is same as a normal distribution. Sometimes I just use both words. Well, now we will generalize it. So for univariate, we have a variance x1, and if we consider the multivariate, so we should just extend it to a matrix, and this matrix we call it as a covariance matrix. Well, then we just have the normal distribution. So the multivariate normal distribution is have the two part. One is our mu, so stand for the expectation. So expectation of this random vector. So just like the x1 and the x2 case, so the mu will corresponding to expectation of x1 and the expectation of x2. And the sigma is something we presented in the formal slides. So therefore, and for the more dimension, like the 3 dimension, our sigma will also increase. So previous here we have the 2 times 2. And if we have the 3, we should describe the 3. We should describe the relation among these 3 random variable. So we have x1, x2, x3. So we also need to describe what is the relation between x1 and x3 and the relation between x2 and x3, okay? So on and so forth. So we have the relation of the x3 with another x1 and x2. So therefore, this covariance matrix is n times n. Once we have a n-dimensional random vector. And if we say, and we for the multivariate normal, we also have this one. So with the mu and a sigma. So whose multivariate normal is defined as this form. So this one is more complicated. So here is just the have the incorporated like the determinant of the covariance matrix and also some quadratic form over the inverse of the covariance matrix. But actually, we just keep in mind, okay? So just give your kind of the explicit form of the normal random variable, or just some kind of the notation presented here. And therefore, so we have already just based on earlier statement. So we already know what is that statement stand for. So what is the stand for the beta hat just follows the normal distribution with the mean beta star with the variance with the covariance matrix I mentioned is a sigma square z times z transpose times z inverse. So it's just a stand for at this moment you take the mu as a beta star and take the sigma as this one. Okay, this is our sigma. Just replace. So it's explicitly told us. So what is the distribution of the beta hat? So just replacing the mu and sigma with these two value. Okay. Well, so just to understand, so what is this statement stand for? So some kind of example. So I will not go to the detail, just left for your reference. And until just demonstrate our result, we will use two important thing. So this I just call it as a true property. So this true property is just the stand. Just want to claim that once we have a normal random variable x, so we can do any linear transformation over the x, and our result is still a normal distribution. So the first statement to say, so given a x is a normal distribution, so it's just some things we have seen before. So what is the density function? So the random variable just fully determined by the density function. And given any a, it's also n dimension, and the inner product between a and x is also a normal random variable. Okay, so a transpose x is give us a one-dimensional vector, so it's become one dimension, and this is also one-dimension mean and also the corresponding variance. So I will not trying to demonstrate, but you here have some example for you can calculate how you given the certain mu and the sigma, how you find the corresponding a transpose x, the distribution of that. So the proof of this one we will not require because this one just have a complicated. It's a little bit complicated if we want to demonstrate this one. Just use this one later on directly. Okay. So the first thing is to say what is we use a matrix, use the two vector time together. So what is the result? So it's still a normal. And the things we should be just know is that what is the mean and what is the standard deviation here. And the next example to say, so given a x also, and also now we just consider, we change the vector a to a capital A matrix. And this moment, so a times x is a new random vector, And then this random vector has the expectation a times mu, has the variance a times covariance matrix a times sigma times a transpose. So some things we should be attention is that this what how the variance is changed. Okay, how the variance is changed. So it's see x has an expectation mu. So ax of course have the expectation a times mu. It's easier to understand, but the variance is a little bit different. So it's a times sigma times a transpose. Okay. Well, next we will try to use these two kind of we have some example also just to mention as your own kind of the reference. We will not go to detail for this part. Okay, now we will just trying to answer. So what is this theory and also trying to demonstrate with the two properties we mentioned. Okay, so now maybe you can also think about for around 1 minute. So one thing I forgot to mention. Okay, so there is a very special kind. There is a important properties in the normal distribution. Okay, so is that once x1 and x2 they are normal random variable. Okay, they are normal random variable. So they are both as a normal distribution. So I use this n to stand for the normal. And x1 and x2, so they are independent. So if and only if the covariance x1 and x2 are 0, so the covariance x1 and x2 are 0. Okay, so now you can just try to utilize this kind of the statement. Okay, to think about. So in this theory, so what is this first statement stand for? So epsilon follows a normal distribution with the mean 0 with a covariance sigma square identity matrix. Okay. So our earlier statement is written down as a, so what is this epsilon here? Is corresponding to once we put the all data together, so we write down as a z times the beta plus the epsilon. So this is a n times 1 vector. Okay, you can think about a while. So what is this stand for? Okay, so the answer is that it states that each epsilon 1 to epsilon n, so they are same distribution. So with normal, let me write down. So it's just stand for, first of all, epsilon 1 to epsilon n. Each of them follow a normal distribution with a mean 0 and with a variance sigma square. And second is stand for epsilon 1 to epsilon n. So are independent. So therefore, this assumption presented here is the same as the assumption I point out when I introduce a normal distribution. Okay, so they are share the normal, so they share the same distribution, and also epsilon 1 to epsilon n are independent. Okay, so maybe we just take some time to understand. So what is it stand for? Okay, why is just stand for this? So epsilon 1 to epsilon n is a vector. It's follow a normal with maybe I open a new page to write. So we have the epsilon, which is epsilon 1 to epsilon n. So it's the statement say that it's a normal distribution. So with a mean or zero vector with a covariance matrix. So it's a sigma square in the identity, in the diagonal part, and zero otherwise. So the first things we're curious about. So is that why the epsilon I, so just why the epsilon 1 to epsilon n as a normal distribution? Why this one is a normal distribution? So actually we can just it's just use our two kind of earlier statement. Okay, so our epsilon 1 could be treated as a inner product between epsilon and a vector a1. So what is the vector a1? A1 is only the first element is 1. The other element is 0. Therefore, the A1 transpose times epsilon 1, not epsilon 1, transpose the epsilon. So is a epsilon. So because A1 only have the first is equal to 1. So taking the inner product, we'll just present the epsilon 1 here. And we also know A1 transpose epsilon will follow a normal distribution. Use our earlier statement. A1 transpose mu A1 transpose sigma times A1. Okay, so A1 is so special, only have the first element is 1, other is 0. So that will corresponding to 0 and sigma square. The epsilon 1 is a normal distribution with this type, just according to our earlier result. And epsilon 2, epsilon 3, you definitely know how to do. Just change the 1 to other index. Okay, just to change the 1 to other index. So therefore, just the answer. So this is just a stand for imply this kind of result. And the second thing is also the same, that so the epsilon 1 and the epsilon n are independent. So the reason is like, we know what is the covariance matrix stand for. So covariance matrix sigma, so it's a n times n matrix, and whose ij's element stand for the covariance between xi and xj. Therefore, once I should use the epsilon. So therefore, once we have the I is not equal to j, which is our off diagonal element, s is 0. Then it's just based on the things I give to you. So yeah, independent. Wow. So here's some kind of so the covariance is very special. Okay, just for the normal distribution, the independent just stand for the covariance equal to 0. So other random variable does not have this property. Okay, so now we have just the answer. So this is just a stand for the same statement. Okay, so don't be confused. We do not add any new kind of the requirement. Just ensure. Okay, just use a different kind of notation here. Okay, different notation. Now, my question is like, how we find the distribution of the beta hat? So we now understand the assumption. Our next thing is how we find the beta hat. How we find beta hat. Now I just put the two properties here together. Okay, two property. And I also write down the epsilon and also the value of the beta hat here. Okay, you can think about how you build the connection with these two properties to find the distribution of the beta hat. You don't need to exactly to compute the result, but so you can just think about how which kind of properties you will use here. Okay, what you will use here. So of course, so just to keep in mind, the important thing is that the randomness only come from the epsilon, and epsilon then contributed to y, and then y contributed to the beta hat. Okay, so therefore we need to trace everything back to the epsilon. How the y depends on epsilon. Y is equal to z beta star, adding the epsilon. Okay, adding the epsilon. So therefore, the good way is that we write down what is z here, what is y here. So this is y. Z beta star adding the epsilon. And then we will have the two term. So the first term we already know it's we can have some cancellation. So it's a function times its inverse. So we cancel each other. So therefore, this result told us what is the relation. So the beta hat and the beta star only have a difference. Is this term. So only have a difference. Z transpose Z inverse times Z transpose epsilon. Well, epsilon is a normal distribution. So you can this is a linear transformation over the epsilon. So the linear transformation just stands for any linear calculation. So linear algebra, all the things in the linear algebra is a linear transformation. Okay, so it's just a matrix and a matrix times epsilon. So at this moment, we treated our A equal to Z transpose Z inverse Z transpose. So this is our A. And epsilon with the mu with then we just utilize this kind of statement. So where our Z transpose Z inverse Z transpose epsilon. So it will be a normal, like, I just use A, okay, just use A. So A is here. So it's A times 0. A times sigma square times the identity times A transpose. So A times 0 will become the 0. And A times sigma square times identity times A transpose we need to calculate, okay? So that will corresponding to, we can first ignore the identity. Actually, just stand for everybody times the identity just stand for its time is still its own value. And sigma square just stand for everybody times the sigma square. So actually this one could be written down at this form. And we have the A is here. And the transpose of Z. Actually, we have used this one before when we handle the projection. So it's first to take the transpose of this part and take the transpose of this part. So that is corresponding to the Z times Z transpose Z inverse. And then we times the Z transpose Z inverse. So it's just corresponding to our covariance. The sigma square Z transpose Z inverse. Okay, so we have already know this part is sigma square Z transpose Z inverse. So this is pretty close to our final answer. Now, the beta hat is equal to beta star, adding this normal random variable, okay? So, and the thing is that, so once the normal distribution, once the constant, add this normal, just making this part change. Okay, just makes the mean change. Okay, so because this one does not have any randomness, so it will not influence the variance, just influence the expectation, just influence the expectation. So eventually, we can make the conclusion. Oh, so where is the conclusion? So we can make the conclusion. So beta hat is a normal distribution with the beta star and with the covariance sigma square Z transpose Z inverse. Okay, so this is pretty just the way mentioned. So the beta star is aware that so for a normal distribution, the beta star is where the mid or the expectation of this random variable, okay, of this random variable. So which means that the expectation of the beta hat is the beta star. Okay, stand for that. So beta hat, even though it's a random variable, but it's average value. So if you can have, if you have you try collect n different data. So there are first the data set, you obtain the beta hat. There are another data set, you obtain another beta hat. You have so many beta hat. Once you take in the average, it will become the beta star. So stand for that the different realization of the data, different data set once you're used, so will corresponding to the same expectation, the beta star, and this can recover our the things the things we desired we want to figure out. And second thing is that it's also but it's a random variable just for a single realization. In reality, you just collect only n data, so you will not have a lot of different data set. Okay, just have a n data, and you but still have some kind of a gap, and this gap is described by the variance, just to show there are some kind of certain things that you may not exactly taking the value as a beta star. Some kind of the second thing we'll take it as a gap. Okay, gap the variance. So naively speaking, our beta hat is just a random variable. So whose mid is a beta star, and also just taking the value around the beta star with some certain variance, with some certain fluctuation. Okay, so and this is for our property too. But there is still one question is like, okay, one question is like, so what is this variance? What is this variance looks like? So what is this variance looks like? Well, so it's we can just for a one dimension case, we can easily to know what is this variance looks like. Okay, just suppose our z is only one dimension, just only one dimension. So if RZ, so it's only equal to Z1 to Zn, just a one dimension. It's a one dimension, and each Zi is a value. And so this stands for each data only have one feature, and we also have a y, just in the very, very simple version. And then the Z transpose Z inverse. Maybe I first write down the already this one. So this one is the summation I from 1 to n Zi square. So Zi square. So therefore, in this version, the beta hat will follow the beta hat is also one dimension, okay? The beta star with the sigma square I from 1 to n Zi square. We probably find the interesting phenomenon. So the phenomenon is that what is the n change will change the result. So once n increasing, that corresponding to we have more and more data. So this term will definitely decrease. So because this one, everybody is positive. So once we have the more n, so this one will increasing. And therefore this whole part will decreasing. So that stands for the variance will decrease. So what is stand for variance of decrease? You will be more and more close to the beta star. You will be more and more close to beta star. So for a random variable, if its variance is zero, just stand for it's a constant. It don't have any fluctuation. It's always around the beta star. Okay. So this therefore, once we have more and more data, it's just told us another kind of phenomenon. When I have more and more data, the beta hat is close to the beta star. Okay, so this is why the big data is necessary, just to guarantee they are become more and more close. Okay. Well, I think, and this is and another example is and so this is just a one answer. So what this is one answer, and another kind of property. So we can take a further step, trying to say how good this estimator it is. How good this estimator it is. Okay, so now we just so here our previous example, our previous property C. So what is the distribution of the beta hat? So it's a least square estimate. Our second property just told us now we focus on a very special random variable, a very special kind of the beta. Okay, we focus on given a certain C. So we want to recover the C transpose beta star. So C transpose beta star. So this is a little bit different compared with earlier one. Okay, so it's for find beta star. Now we just consider C transpose with beta star. So you may just keep wondering, so why we need that? Because we can take in the C as a 1, 0, and 1, starting with the 1 and other element 0. And in this case, the C transpose beta star just equal to the beta star 1. Okay, the first element. So now the people just wondering, so we want to find the C transpose beta star. And of course, a straightforward answer is that we will use the C transpose beta hat, right? C transpose beta hat. And this theory, so Gauss-Markov theory, just told us how good the C transpose beta hat it is, how good it is. Okay, so maybe we can see this one directly. Okay, so this statement is a little bit complicated. So we consider the C transpose beta hat so as a estimator for the C transpose beta star, want to recover that. So and this estimator has the smallest possible variance among all linear estimator of the form which have this kind of the style that are unbiased with the C transpose beta star. Okay, so first of all, let's understand this one sentence by sentence. Okay, so now of course the C transpose beta star is the estimator for the C transpose. C transpose beta hat is the estimator for C transpose beta star. And now we're just wondering if we can further write down the C transpose beta hat, so it can be write down as a C transpose Z times Z transpose times Z inverse Z transpose Y. So we're actually this type of estimator is a linear combination of our Y. So it's some metric, some kind of vector. So this is a vector. So this part is a vector times the Y. So therefore, our C transpose beta hat could be regarded as the linear combination of our observation Y. Okay, observation of Y. And now what we want to do is that we want to show that any other linear combination you try into any other matrix A, any other vector A, so which corresponding to A transpose Y, also as an estimator for the C transpose beta star. This one is the best choice. Okay, so let me emphasize, C transpose beta hat has a form like a vector times A times Y. And now we're just wondering, so whether we can change this part to create another estimator for C transpose beta star. Okay, we just want to change this one with any arbitrary A. And this one is the best one. Oh, this one, so this part is the best one. Okay, the A must choosing at this form. So it will be the best one estimator. And what is the best one state? So how we make a criteria on the best estimator. So it's just to have the two stamp. So first, that is unbiased. Second, first it's unbiased. Second, it has the smallest variance. Smallest variance. Well, so this series just to take a further step. The first one just told us how the beta star, how the beta hat play an estimator as a beta star. Well, it's a normal, and whose mean is a beta star. And the second one is that if we consider any other estimator, this beta hat will be the best. Okay, now maybe we just take some time to see, so what is these two things stand for? Okay. So the unbiased term. So now we just think about, we have a estimator like the beta star. This is our parameter beta star. We have the several estimator, beta hat, beta tilde, and some other maybe just these two. And we want to know which one is the best. Which one is the best? Where is the criteria for the best estimator? Both of them maybe are a random variable. So the criteria we will see in this kind of theory just follows this kind of consideration. First of all, the expectation of the beta hat must equal to beta star. Expectation of the beta tilde must equal to beta star. So this we call it as a unbiased. So which means that even though it's a random variable, but it's a mean, it's still as our target. And second criteria is that, so first of all, we just consider, so if there are some other vector, like the beta bar, and if its expectation is not equal to beta star, so then it will be, we will just exclude the beta bar. Okay, exclude the beta bar. So the first step just trying to guarantee the beta hat and the beta tilde, so they are unbiased. So it's the expectation beta star. So it's quite makes sense. Okay, quite makes sense. And second thing is that both of them, if they are unbiased, we want to take a further criteria on them. So the best one will have we just compare the variance. So the best one will be the estimator have the small variance. Just for example, beta hat have the smaller variance. Then the winner will be the beta hat. This is just because now both of them have the expectation beta star. We know they are around the beta star, but the good estimator must be more close to the beta star. So even though it's around the beta star, but it also have the distance between the beta hat and the beta star. So the best one must have the smaller variance. Okay, have the smaller variance. So this is just a criteria. First, expectation is equal to our target. Second, have the smallest variance. Okay. So this key idea just the people how they just identify a good estimator, and this result just say this one it is just have the smallest variance compared with all other unbiased estimator. So you can propose the lots of unbiased estimator, but this one is the one that have the smallest variance. So therefore, this statement just trying to say the beta hat is the best estimator for the beta star under the criteria of these two. Okay, these two criteria. Okay, maybe we just take a break. So this is one type of criteria. In the chapter 3, we will see another type of criteria. Okay. So this we have already used this kind of the Gauss-Markov theory to state how good this beta hat, the least square estimate it is. Okay. So we're now trying to show this one. So just because this also just have a lot of kind of things if we want to show this in detail. I also list some kind of the for your reference. So if you have an interest about that. So this demonstration is not such kind of straightforward because at this moment you need to try to describe any other arbitrary unbiased estimator will also lead into the large variance compared with the variance we proposed here, compared with the variance we proposed from the C transpose beta hat. Okay, so but just keep in mind, so this is some usual case to answer how good the least square estimate it is. Now we will just to also answer another question. Also, I put earlier before. So I mentioned that so epsilon actually is not necessary to be a normal. So we mentioned that the assumption that epsilon 1 to epsilon n follow a normal distribution could be changed as a expectation of epsilon I is 0. Variance epsilon I is a sigma square. So it could be changed, okay? So we do not require as a normal just because we know the normal is so special. Normal is so special. So is you can of course you can define any other arbitrary random variable. So it may not follow the curve like a normal. So therefore, of course, in reality, if you understand more about the probability, you can understand how this assumption strong it is. You require something unknown follow some certain pattern. Okay, follow some certain pattern. So it's pretty hard to demonstrate. So therefore, we need to relax this assumption. And once we relax the assumption that we only require the noise is 0, with the mean 0 with the variance sigma square. So no longer like a normal. Normal also told you so how the probability it is, but here you don't know. It's not necessary to know what is the probability it is. Okay, so I hope you can just catch up. So this just also require. So underlying assumption is also required. So what is the density function of this epsilon? But here we no longer require what is the density function of the epsilon. Okay, we no longer require the density function of the epsilon. It could be any other arbitrary distribution. And at this moment, so if the epsilon is not normal, our result will be right now at this part. So once n is close to infinity, the beta hat will also become this normal distribution. Okay. So this beta hat, we can also write down this one again. So according to once we make use of y equals to z times beta star adding the epsilon, so the beta hat we already know is the beta star adding the z transpose z inverse z transpose epsilon. So at this moment, the epsilon is no longer a normal distribution, but the interesting phenomenon is that this term will also become a normal distribution, even though epsilon is not normal distribution. Okay, so it still becomes a normal distribution. So this kind of statement we just use a central limit theory to demonstrate. Okay, central limit theory just told us one phenomenon. Once we adding a lot of randomness together, it will become a normal distribution. So that is the normal distribution. Why it's important. Sometimes we also call it as a universality. So universality just stands for it's just a common kind of result. Once you're adding a lot of noise together, it's a normal distribution. Okay, so therefore, why sometimes the people will have assumption like the normal. So just because when we're just taking our observation, making our sampling, so the noise may come from everywhere. So it's a lot of noise and combined together. So therefore, you can assume that once you collect the data, such kind of noise is normal. So this is why the people can just use this normal distribution sometimes could be acceptable just because of this reason. So we have several kind of unknown influence things will unknown term will influence, but once they add it together, it's a normal distribution. Well, so therefore, once we handle our own data, once we use our own package, why it still have the p-value? Just because the p-value itself come from the normal, just come from normal. We will explain it later. But why we don't have the we do not have this assumption, we can still create the normal distribution to calculate the p-value just because of this result. And here it have a phenomenon that require n is equals to infinity. But in most of the case, this n is not such kind of large. It can guarantee this one is close enough to the normal distributions. Commonly, people will say, told you some kind of practical criteria like n is like 30, n is like 50. So such kind of value is able to guarantee it's pretty close to normal. Okay, so it's some practical kind of the implementation. Well, so this is just the answer or my earlier statement. Okay, my earlier statement. So that is we do not require epsilon is a normal, so it can still get our least square estimate is still a normal distribution. So this is different compared with our earlier result. Our earlier result say that beta hat is follow a normal distribution right down at this one. So this follow just stand for the equal, okay? So here it's just become close to normal. And once epsilon is the normal, it's this beta hat is exactly the normal. But here it's just become more and more close to normal. So the only difference is here. And now we still have one remaining issue, is that so in addition to the beta star, we don't know what is the sigma square. Sigma square is come from the sigma square is come from, so come from which part? So come from our noise, epsilon. So how we estimate the sigma square? How we estimate sigma square? So if we want to know the variance, so z transpose z we know, but what is the sigma square? So commonly we will use this one to estimate the sigma square. So it's 1 over n y hat minus y. Y hat stand for z times beta hat. Okay, so this is a y hat. Y is itself is our data. So more just to write down this one in detail. So this is like the z times z transpose z inverse z transpose y. Okay, so this is how we estimate the sigma square at this moment. So commonly it's just like to say it's prediction error. So this is a prediction error. So this term is our prediction. This term is our target. The prediction error just describes the noise. Because this y hat can be treated as a z beta part. Y is part with the z beta part at the epsilon. So therefore, the difference between them just told us how epsilon it is. Once you're taking this one, it can be treated as the estimate of the sigma square. So I will not just go to detail, but if you have interest, you can also ask this part later. Okay, this part later. So it's also some other kind of the things that so this also is a valid one. You can demonstrate. So this one is the expectation of this one is close to the sigma square. The expectation of this one is close to sigma square. Well, now we will just put the earlier my earlier kind of scenario I have described to you. So this is the things when we first trying to mention the property 2. So what is the reason to mention the property 2? So this before that, so once we adopt the linear model, so with different package, so it will commonly give you the estimation error. So estimation error. So it's come from here, coefficient part, and also give you a standard error. So which is our sigma square z transpose z inverse. But sigma square is also estimate, just as I presented here. So this is how we estimate. Once we have the sigma square estimate, so we can just estimate this part. So in a common package, it will give you the coefficient part. So this corresponding to our beta hat. And also give us the standard error. So that corresponding to the diagonal element of the sigma hat Z transpose Z inverse. But some more often case give you a p-value, So how we understand this p-value? So here I do not want to distinguish the p-value with the t distribution, but they are sometimes once you have enough data, they are so close. Okay, so we just mention. So what is this p-value? Okay. Now our earlier statement is like, so we have the y equal to z beta star, adding the epsilon, and we want to recover the beta star. So maybe in some simple example, like y equal to beta star 0 plus beta star 1 z1 plus beta star 2 z2, adding the epsilon. So I just decompose this z as only 2 feature. And usually, so our commonly there when we do the regression, okay, so we have a purpose like make a good prediction. And in some kind of scenario, we also want to have more understanding about the relation. We want to understand what is the relation between Z1 and Y. So this Z1 is a little difference notation, okay, just stand for the first feature. And this stands for second feature. We want to know whether the first feature will have the influence on the Y. So this feature may be stand for some new drug. Stand for the whether the patient takes a new drug will have the influence on its healthy part. Okay, healthy part. The drug. So Z1 can equal to 1, maybe stand for the person takes the drug. Z1 equal to 0 just stand for the person does not take the drug. So in this kind of the scenario I describe, the beta star 1 just stand for what if the influence of the drug? What is the influence of the drug? Okay, so just because once it takes the drug, so this one, if this one is non-zero, it's positive, just stand for it have the positive contribute to Y. If it's negative, just stand for the negative contribute to Y. And if 0, it just stand for have nothing to Y. So therefore, in the clinical trial, in the clinical trial question I mentioned, the key important things is trying to answer whether this term is 0. So whether this term is 0. So then we can know how about our new invented drug. Okay, have some information about how our new invented drug. So it's a little bit compared with the prediction problem we mentioned. We focus on a single variate, single coefficient. We're wondering what is that. Of course, so I mentioned earlier, the beta hat. Of course, we don't know what is the beta star 1. So even though we collect data, we still don't know. We just can find a beta hat 1. This stand our beta hat, I just write down as a beta hat 0, beta hat 1, beta hat 2. What we can only observe is the beta hat 1. So, and we know they may have some kind of discrepancy. So they may not just equal. So the question is just like to answer, I mentioned before. In the case 1, so case, I find the beta hat 1 is 0.1. So I would like to answer whether the beta star 1 is 0 or not. It's pretty hard question because they are so close. Okay, they are so close. And in case 2, like beta 1 hat is equal to 10. So they are so different. But we are still not such kind of certain about whether they are different enough, whether their difference is enough. So therefore, the common question is trying to ask, so what is the difference between this value and 0? Okay, what is this difference between this value and 0? So we can have a feeling that maybe this one is pretty large, like the 10, we can say they are not 0. Like this one is small, we can say it's not 0. But of course, it's not a scientific approach. Okay, it's not a scientific approach. The scientific approach is trying to see, now, we will try to do this one, prove this one by contradiction. The proof by contradiction is a usual case that first we assume this term is true, and then we will try to find whether there are any counterexample. So if we can find a counterexample, then our assumption is wrong. Okay, so it stands for the proof by contradiction. So we first assume it's true, and then we can try to find counterexample. Once we can find, then our assumption is wrong. So this is a usual case. Now, just for example, either in the case 1 or case 2, I first assume that beta star 0, beta star 1 is equal to 0. And then I can easily to figure out. So this term will close to a normal distribution with a mean 0 and with a corresponding variance. So for example, I use a sigma 1 square. And if we, of course, we can compute what is the sigma 1 here. So we know it's just come from the, so this sigma 1 just from that sigma square z transpose z inverse matrix. So which is a 3 times 3 part. So here we have 3 elements. And this is a sigma 0 square, sigma 1 square, sigma 2 square, and some other element. So some other element stand for the covariance. So therefore, this term have the variance is coming from here. And we can just use a sigma 1 hat to calculate. So this is why the earlier table we can find have the standard error. Why the earlier table we have the standard error. Okay. So this is standard error stand for sigma 0, sigma 1. And now we can find the beta 1 hat is become normal 0 with sigma 1 square. Okay. Maybe I use a hat. So just suppose in case 1, our sigma 1 is equal to pretty small value. In my second question, case 2, our sigma 1 is equal to 10. And now, in case 1, we know this 0.1 is sample from this distribution. Our beta 1 hat equal to 0.1 is from a normal 0 with 0.001 square. In our case 2, beta 1 hat equal to 10 is sample from normal with 0, the power of 10. Okay. So therefore, we can actually find a contradiction, find the counterexample. This one is proper, this term is actually has a very slow chance to happen. Very slow chance to happen. The p-value we mentioned in the previous table is just stand for what is the probability that you can sample this value from this normal distribution. So with the mean 0, with the variance, the standard error square. Okay. And second one is also the same. That's for the 10, it will have a very high chance that you can sample from here. Just because you have a large variance, and then you have the chance to sample the 10. So even though the 0 is just this 10 is so different compared with this 10. So these two things are too different. But the standard error, if it's large, it is still the chance you can take in this 10. Just because a large standard error. Okay. So therefore, the p-value just trying to compute under this normal distribution, what is the chance you can sample? Under this normal distribution, what is the chance you can sample? So you can say it's just a stand for a probability larger than 10. Probability larger than 10. So in the case 1, so this one just stand for the probability that normal distribution will larger than 0.001 I forget the value, 0.01 probability. So stand for the corresponding normal we have mentioned here larger than the absolute value of the 0.1. And in the second example, just also say that kind of normal larger than value of the 10. Back a little bit, okay? So stand for the probability that the normal larger than the beta 1 absolute value, okay? So this one just corresponding to our p-value. So here maybe sometimes there are some kind of little modification like the t-distribution, but I don't want to figure out the difference here. They are some, in most of the cases, they are so close. They are so close to each other. Therefore, now we can just back to this example. We can take this one again as an example. So now this model is considered such kind of model. So where we only have the two feature, y is equal to beta star 0 plus beta star 1, C1, adding the noise. Beta star 0 is estimated with this one. So this is our beta hat 0. So this is our beta hat 1. So beta hat 0 is 0.11, and second one is close to 3. So with a corresponding standard error. And p-value is also presented. So if p-value is large, just like the 25%, in the first example, just stand for you still have the 25%. You can just sample this value according to a random variable, normal random variable with a mean 0 with a standard error here, and so therefore you still have the 25% chance. So in common case, we will say 25% is still some acceptable one. So if this one is pretty small, like only smaller than 5%, we will say that the things will be a real case. So that could be made as a counter example. So the p-value here is a 0.253. So which means that it still have the chance that this beta star 0 is exactly 0. So it's a 25%, something like that. But for the second part, we can find p-value is almost 0. Stand for it's very real case that you can sample this value according to a normal distribution with a mean 0 with a standard error here. Okay, very small chance. So in reality, so this p-value is more, just stand for this term is the corresponding ground truth is significant with 0. Okay, it's not 0. So this is another kind of phenomenon we should be care about. So what is the p-value here stand for? It's also a direct application of our property too. So this also told us in sometimes we may not only focus on the prediction. In some kind of scenario, we also need to understand how uncertainty come from our data, how uncertainty come from data. So it have some uncertainty, okay? Wow, so this commonly, so we will not focus too much, but just taking this one as an example. So this commonly comes from the statistical part, we call it as a hypothesis testing. So we just assume this one first, taking as a hypothesis, and then we're trying to find the counter example. Okay, so far, any question? So this kind of thing is just truly will be often used in the scenario field like the biomedical in the finance part. So but in most of deep learning part, you don't necessary to compute the uncertainty, okay? Because that model is exactly the black box, okay? Exactly black box. So you don't have such kind of so given the deep learning model, you don't have any kind of understanding about how the Z contribute to Y. So we call it as a black box. But here it's not black box. You have a clear understanding about how Z contribute to Y. So in some finance kind of the data, people will care about just because like you want to do some kind of the factor analysis. So it's your factor, and this is some kind of your target, some your kind of the target. So you want to know whether this factor is useful or not. So therefore, you should to understanding whether this one is 0 or not. Okay, some factor analysis part. So sometimes it's also corresponding to the cross section in the finance data. Well, so just some certain application. So because in some kind of scenario, so the understanding is also important. Well, we will end this chapter with introducing another estimator, so which called as a maximum likelihood estimator. Well, we will meet this often. So once we handle the classification problem, so like if you have used before, like the entropy loss, it actually come from the maximum likelihood estimate, entropy loss. Well, just before that, let me ask you a simple question. Okay, let me ask you a simple question to introduce this maximum likelihood estimate. So we use it right down as a MLE. Now I just consider, I want to estimate the probability that tomorrow is a raining day. So we know, I assume that P is a stand for tomorrow is a raining day. Okay, it's a raining day. And 1 minus P stand for it's not a raining day. So I just want, this is just for the simple example to understand what is MLE stand for. And now I can observe there are 4 data, maybe 3 data for simple. Okay, I can observe there are 3 days historical. So, and there are 2 raining day. And 1 is not raining. Okay. Just based on this simple idea, simple data. So what is about the value of the P? P just stands for the probability of the raining day. And E minus 1 minus P just stand for it's not a raining day. And now I just you answer. So what is the value of the P? Just based on the data. So of course it's an estimate of the P. You definitely know the answer, okay? So it's nothing, it's the answer is just like 2/3. So it's very simple, okay? You just consider there are 2 raining days and 3 in total. So you choose the 2/3. But here we will try to use another way to understanding how this 2/3 come to our mind. Why it's the answer. So the answer is just based on this kind of thinking, okay? We will use another angle to figure out this 2/3. So here you can see it's just the average, but here we will use another way to answer, okay? So now, actually, I can observe there are 2 raining days and 1 is not raining. So which means that in my observation, 2 raining days happens with probability P times P. First day raining and second day is raining, and the last day is not raining. So I can calculate the probability that these 3 events happen together. P times 1 minus P. Okay, so just because I know it's raining, so raining, not raining. So therefore, if we times the certain probability together, this one will commonly called as a likelihood function. Likelihood function. Just stand for, I have 3 data, and I want to know what is the probability that this data can happen. So what is the probability that raining day will happen? So it's a P. Not raining day is 1 minus P. So therefore, the likelihood just becomes the P with the power of 2 minus the P with power of 3. And my question is looks like, so how this P is equal to 2/3? So this is based on the thinking that, so we were trying to maximize the likelihood. So this is the probability of our event, but we are uncertain about the P. We are uncertain about this value of P. I want to know what is the value of the P. So I first just use this P, treat it as some unknown variable, and then I directly calculate the corresponding probability, overall probability according to our data set. So it's just given as a P squared minus cubic of P. And but one thing we know, this probability is something already happened. That just stand for, if I choosing another value of P, I need to guarantee this something already happened has the largest probability. So the MLE is just trying to see the P hat is the argmax of the P square minus the cubic of P. So how we just find the maximum. So we also do the derivative, okay? So we obtain that 2p minus 3p squared. We want to make this guy equal to 0. And we only have two solutions, p equal to 0 or p equal to 2 over 3. Okay. So this is how the 2 over 3 come from. Okay. So the reason is just like, so it will not be 0. You can just take in 2 over 3 and 0. You find that the 2 over 3 has a large value. So this one will 2 over 3. So which means that we are trying to have this kind of the thinking that we choose the 2 over 3 to make something already happen, have the largest probability, largest likelihood. This is just a core likelihood, but they are just stand for the probability time together. So 2 over 3 just corresponding to the thing we're making something already happen, have the largest probability. Okay, so this is how we combine it with the 2 over 3. So just this kind of straightforward generalization. And now our question will become a little more complicated. Now my data is not looks like here. My data is given as a, I also use the blue, okay. Is a zi and yi, I from 1 to n. And we also know how the noise is come from. What is the random thing come from? Random thing come from our epsilon. So only epsilon has the probability. Well, I should use the yi. So this is our data. And what we're trying to estimate is the beta star, and epsilon is our randomness. So therefore, we can find that our yi minus the zi transpose beta star is our epsilon I, okay, is our epsilon I. And now I have the n data. I can calculate the probability that epsilon I equal to this term. So we just want to estimate the beta star. Now I just treated as this one as unknown. I want to try what is the case that I try any different beta. So what is the probability of the epsilon I? Epsilon I itself is follow a normal distribution here. So who's the density function? Is here. And once we know the beta, we can of course find what is the value of epsilon I. So because epsilon I just yi minus zi transpose beta star. So this is just the same things I mentioned. Once you know the p, you can directly compute what is the probability of the tomorrow is a raining day. Once you know the beta, you can definitely know what is the probability of this random noise happen. This random noise happen. You can know the random noise. And also epsilon I just told you, this function just told you, what if the value, if you take in the epsilon I, so with a certain probability, you just replace the x with the epsilon I. So therefore, at this moment, our likelihood function, usually we will use the L beta. Actually, we also have the sigma is also some our unknown things. Okay, both things I write together here. So it's a product f epsilon I, f epsilon I. We can further write down this one as a f yi minus zi transpose beta. Okay, so this is our likelihood. So we already know. So given any beta and the sigma, we can find the corresponding likelihood. So therefore, the MLE just stands for beta hat and sigma square hat equal to the argmax of the L beta sigma square. So in this kind of example, what we are trying to do is trying to show this one is exactly same as the least square estimate. So this one is same as the least square estimate, but we will take some time to do, okay? Take some time to do it. But usually, sometimes we will find it's very disappointed to handle with a product. So usually we will taking a logarithm first, taking a logarithm. So which means that we will commonly will not directly focus on maximize the L. We focus on maximize the logarithm of the L. So natural logarithm. Okay. Usually this one stands for, so maybe a little bit come from with, so this one just stands for, okay. Usually stand for this version. Okay, stand for this version. So logarithm with the base of the E, with the base of the E, okay. Exponential part. Now, I just want to calculate this one. So the logarithm of this one is stand for the argmax summation I from 1 to n. The logarithm of f yi minus zi transpose beta. Okay, so it's not necessary to trying to it's not necessary to just calculate by yourself. I just want to show the procedures. Okay, so we should to understand. So this is another type, a very straightforward approach to presenting another type of estimator. So it's very, very standard approach. And then we can write down the argmax. The logarithm of the first this term will create into two parts. Okay. The first, this is 1 over square root of 2 pi sigma squared becomes this two term and minus, it's not x, it's a yi minus zi transpose beta 2 sigma squared, 2 sigma squared. And then this is the argmax we want to do. We have the two things to argmax. So beta and sigma squared. So you probably have the answer about how we find the argmax of the beta. Okay. We just focus on the term only have the sigma, only have the beta is this term. So once we taking the summation together, we will quite meet our answer. So if we want to argmax beta, we're just trying to argmax this thing. These things you know the answer. What is the, well, I just forget to have a square here. We have a square here, stand for x square. So what is the argmax of this term? The least square estimate. So just because this is our least square, so we want argmax the negative least square just stand for we want to find the mean of this term, the minimum of this term. So this stand for the least square estimate. And for the sigma square, now we're just taking the derivative for the sigma square. So we just keep on where is the term have the sigma square? Where is the term as the sigma square? So I will left as an exercise for you. Okay, left as an exercise for you. So eventually the sigma hat square will become y hat minus y. Okay, sigma hat will become y hat minus y. This is the answer. So I will left for you trying how to take the sigma square derivative to find the answer is this. So I just have some very, very brief. I don't have that kind of detailed answer. Okay, I don't have this detailed answer. But just left the exercise for you. Okay, so taking the here the things is that you treat the sigma square together, and trying to find the solution. Well, so eventually we have this answer. So the MLE estimate. So another estimate that we find the likelihood and trying to find the argmax is same as the least square estimate. So when the epsilon is our normal distribution. So, but of course, in other cases, they may not same. They may not same. Okay, just in this version. And the MLE is important just because it stands for it's also another type of good estimator and also have the so and also have a kind of lots of kind of properties. So therefore, in lots of classification problem, so once you want to identify the error, identify your objective function, you just use a maximum likelihood approach to identify the error. So therefore, if you later on, if you're trying to see some deep learning model or some other kind of some deep learning paper, so you can find most of the cases they will mention a likelihood function. So that is a way trying to define the objective or loss function. So in your model. So we will meet it later. So once we handle with the classification part, okay. Maybe we just take another 10 minutes break and we will go to chapter 3 next. And we will starting with our chapter 3. So chapter 3 will contain a lot of kind of the calculation, but actually we not required, so you are not required to just trying to recompute by yourself. So but trying to understand it, okay? So the chapter 3 we will focus on two type of thing. So the ridge and the lasso as a two kind of alternative estimate for the least square estimate. And but of course, the main idea is that main thinking is that so why we need two? So we have already seen the least square is pretty good. Why we need two another two, the ridge and the lasso. So and today's we will focus on the ridge and trying to give you some extreme case where the least square will have the worst result. Okay, have the worst result compared with the ridge. So this type of thing sometimes will calculate a little complicated. So, but don't worry, okay. So if once you meet the problem, you can free to ask. So the calculation contain a lot of knowledge in the linear algebra, even though we have a review them. But actually not required to calculate, not required, but we should try to understand. So how the procedures, why we need this new two additional estimate. So the least square estimate when we first look at, so we have assumption that Z transpose Z should be invertible. So these things can guarantee that we can find the least square estimate just because we need to consider the inverse. And the natural question is that, so what if this, and also just one trouble is that once this one have the small eigenvalue. So invertible just the claim that lambda 1 to the eigenvalue are or actually is r plus 1 is all positive. Actually, should no non-zero. But for this special matrix, their eigenvalue is always positive, just in this special eigenvalue. Okay, special matrix. Z transpose Z just whose eigenvalue is always large or equal to 0. And but there are some cases that this lambda 1, even though it's non-zero, but it's pretty close to 0. In some reality, we could have this phenomenon. Some lambda I are close to 0. And this is the reason why we will use the ridge regression. We will see example later. Once the lambda I is close to 0, this one is arbitrary large. And then the beta hat is arbitrary large. So you don't expect, so you have some data that x and y are some usual value, just like the all the value are smaller than 10. And you just find a beta hat is 10,000. Well, you must notice that there are something wrong happen. Okay, your data is just some small value, but you just find a beta hat is 10,000. That's something. Well, we will believe there are some bug in our algorithm. Well, and this kind of things is sometimes so. Just want to answer the question. So what if the eigenvalues of Z transpose Z is close to 0? So just like I mentioned, the inverse just want to making the inverse on the eigenvalue. So therefore, if eigenvalue is close to 0, then this inverse just will be, so like we're taking some 1 over some term, which well very small. This term will become extremely large. The example is given here. So we consider, this is the usual case, that we consider our y and x. So it's a one dimension with one feature. And this is my model. It's true model. This is the beta star 0. So beta star 0 and beta star 1 is equal to 1. So this model stand for. So I also adopted the Python package trying to find the least square estimate. We can find the coefficient of them, the constant stand for our beta hat 0 and beta hat 1. Oh, they are just something pretty good. So we know that the ground truth is 1. Okay, ground truth is 1. And we find these two are close to 1. So therefore, just stand for everything is usual. Okay, everything is usual. So it's just the same matches the same phenomenon in our chapter 2. So the both of estimation is close to the ground truth. But now I just want to do a little bit kind of the change on our data. So now I just add additional data. X2. Well, just wait a minute. So I just add additional data. X2 here. So where X2 is X1 plus epsilon 2. So some noise adding in the X1, which will become our X2. At this moment, my model Y is also generated from 1 over X1 plus epsilon 1. But of course, we have no idea about that whether X2 contribute to our Y or not. But once you do your own kind of research, you're just trying to collect all the feature. Okay, just you have the X1, have the X2, so you just put them together. So this is how the Y's come from. So it comes from 1 plus X1 plus epsilon 1. And the X2 is just some kind of the duplicate with some noise on the X1, but they are just a little different. But now we have no idea about that. So we just collect all the feature X1, X2. And we're trying to do the least square estimate. And this is our result. So of course, what we expect is that this guy could equal to 1, this guy could equal to close to 1, and this guy could equal close to 0. So, but unfortunately, we cannot make this thing happen. So we just find x1 is -5 and x2 is 6. So this is the phenomenon we mentioned that corresponding to the case. Once we adopted this x1 and x2, we will have an issue that their eigenvalue, they will contribute z transpose z, and the eigenvalue of z transpose z is pretty small. So just in this kind of special case. So this will just the scenario where we have the small eigenvalue. It just stands for some of our feature are close, are very similar. Some feature are very similar that will make z transpose z. Z transpose z has a small eigenvalue. Okay, so even though you can find prediction may be good, okay, just like the -1 and 6 adding together is just like a 1, but actually this is something we do not expect. Okay, well, so therefore, let me see whether I give you some example for that. Okay, I will put it on the rich part. So this example trying to see, so the case, so once x1 and x2 they are close to each other, then the eigenvalue is small. And now we want to do a further to explain. So why that eigenvalue small will cause this phenomenon that our estimate is unstable. Why our estimate is unstable. So we will try to use a singular value decomposition to answer how the z transpose z have the small eigenvalue to make our beta hats, the least square estimate, have a large value. So maybe I put our things here. So we will use this one. We will use this singular value decomposition to describe why the z transpose z have the small eigenvalue will lead to large beta hat. And later on, we will also to indicate, so when is the case that will have the small eigenvalue. So our question is two type, okay? Two part. The one is how the small eigenvalue cause a large beta hat. Another is when we will make the small eigenvalue. So small eigenvalue I mentioned is just the feature they are same. Feature they are same. Just like x1 and x2, they are two features. They are so close to each other, so whose eigenvalue will also be small. And now, so Z transpose Z, of course, in our expectation, it may have small eigenvalue, just like I mentioned. The inverse will have large eigenvalue, and then making our beta hat is extremely large. But we want to make it more we want to ensure that to do some calculation, give some mathematical explicit form, and then we can understand how why the reason it's like. So the reason when we look at the beta hat, so it looks like here. So when this eigenvalue is small, so this one is large, this one is small. So how we just combine the small eigenvalue and a large eigenvalue and a small one will combine together. So what is the eventual outcome? So this is something we want to understand. Okay. So now we will introduce a thing called as a singular value decomposition. Singular value decomposition commonly is just introduced with the principal component analysis. Okay. Here we just focus on this one. Okay. So here it stands for a matrix A could be decomposed as three parts. U times sigma times V transpose. So U is a orthogonal matrix, sigma is a diagonal matrix, and V is also a orthogonal matrix. So it's considered for any kind of the matrix which is with the size m times n. It could be treated as a m times m orthogonal matrix, m times n version diagonal matrix. We will see what is this diagonal later, and n times m, n times n orthogonal matrix. So orthogonal matrix we have used before. Then for that identity matrix. So U transpose U is identity. So with it's a M identity. Okay. V transpose V is a N identity. And then the diagonal element within this part, we will call as a singular value of the A, called as the singular value of the A. The singular value. Okay. So don't confuse about this kind of SVD. This SVD is just quite close to the spectral decomposition we have mentioned in the chapter 2. So orthogonal is not our first time to see. Just to have a review about the spectral decomposition. Well, that is state for any matrix. I should use a B. Okay, for any matrix B. So who is the symmetric? B is equal to B transpose. And then spectral decomposition told us B will equal to, I make it as M times M, okay, will equal to U times the diagonal matrix. So who with the diagonal is eigenvalue times the U transpose. Okay, so this is a spectral decomposition for a symmetric one. B will equal to the orthogonal matrix U times the diagonal times the U transpose. So this one is pretty looks like compared with this one, just so close. But let me just give you some insight about so what they are actually just stand for the same things. They are just exactly the same. So just because when the people handle this singular value decomposition, so A is any matrix, here B is a square matrix and also symmetric. So how the people just generate a matrix. So here, when you consider A is M times N, you will directly have a symmetric one, so which is A times A transpose. So it's M times M. And this one, also the transpose is equal to itself. Stand for this one is symmetric. Then you can apply the spectral decomposition. Let me write down. It's a U diagonal eigenvalue times the U transpose. So therefore, this is a spectral decomposition. And then the people will wondering, so wow, they are just like the A square, A times A. So like the A square. Can we just decompose this one again? I will decompose this one again. So therefore, they have a new breaking. They just splitting this eigenvalue to two parts. Splitting the eigenvalue to two parts. That is our U. The sigma here, the V transpose, and times the V times the sigma transpose times the U transpose. Okay. So I didn't mention how the splitting is, but when I apply our example, we will see here. So here, just they do some splitting. And then you will have the A is this part. A transpose is this part. So you can see, so it's just a breaking over this diagonal part. Will create into this sigma V transpose. So therefore, even though just in like a lot of linear algebra, the people will say the singular value and the eigenvalue, but we probably know what is the difference. Okay. How you just breaking the lambda 1 to lambda m to the 2 sigma. So it's a square root. Okay. Singular value is the square root of the eigenvalue. So they are same. So actually, don't confuse about that. They are just one takes the square root will give the singular value. Well, so what I want to say is that this one is the same as, well, I just want to build some connection. So we will not just use these things directly. So I just want to tell you some connection. So we will use this HVD to answer. How's the beta hat? How the sigma play a role here? How the singular value play a role here? Well, I actually have a detailed solution here. So here we consider our Z is n times r plus 1 matrix. We can do the singular value decomposition. So where U is n times n, V transpose is r plus 1 times r plus 1. And sigma is our n times r plus 1. So this sigma is not a square matrix. It's with it has the column and have the row here. And actually this is a column, this is a row. Okay. And then what we're trying to do is that we are trying to write down this sigma. And this sigma is just has a diagonal element is a singular value. So just because n is larger than r plus 1, so commonly we will have this type of the rectangle, okay, this type of rectangle. So here is our U. You can forget about anything about the element here. We will not use this one directly. So just write down as a U. And also another part is our V transpose. Don't worry about this part. So we will not use this one directly, just write down as a V. Here, just to give you the detail format. And the sigma, some things we should pay attention is n times r plus 1. So whose diagonal element is non-zero? So with the sigma 1 to sigma r plus 1. And the lower part is all 0. So if I can, so this is our sigma looks like. And this small sigma, this is I call it as a capital sigma, okay? So this is a small sigma. So the sigma here is stand for the singular value. So singular value. And then now at this moment, I want to utilize the form of Z to compute what is the Z transpose Z inverse times Z transpose times Y. Okay, I just want to calculate this one. So we will focus on the Z transpose Z first. Z transpose Z is easy to handle just because it's a U time. So just because Z itself is equal to U times sigma times V transpose. Z transpose will become V times sigma transpose times U transpose. So therefore, we combine the two together. We will obtain this one is a V times sigma transpose times sigma times, well, V transpose. Okay. The orthogonal just can cancel with each other. Well, what is the sigma transpose times the sigma? You can image that we have another matrix. It's also with the sigma 1. It just looks like the sigma, well, the sigma looks like sigma 1 to sigma r plus 1, 0, 0, and all remaining element here, 0. And the sigma transpose looks like sigma 1 to sigma r plus 1, 0, 0, and all 0 in the remaining part. So therefore, the sigma transpose sigma is a diagonal matrix whose size is r plus 1 times r plus 1. So actually, I should write down the full size. So with the or element is a sigma square to sigma r plus 1 square. So you don't need to copy. I just also have the answer directly show here. Okay. So Z transpose Z is the V times the diagonal times the V transpose. So this is the things I mentioned. This is a form of the spectral decomposition. And then, so this therefore the num sigma 1 square to sigma r plus 1 square is exactly matching the eigenvalue. They are just the eigenvalue, lambda 1 to lambda r plus 1. And our target is trying to find the inverse of this term. You can try by yourself. Okay, inverse is exactly here. Inverse is exactly. You're taking the 1 over sigma that will create the inverse. So the easy to say is that once you use this term times this term, you will obtain an identity matrix. They are common trick. So common trick. Just because the way is orthogonal, the common trick is the inverse, just taking the inverse on the diagonal part. And then we already find the Z transpose Z inverse. And because we want to use this one further times the Z transpose Y. So we times the Z transpose also. So you can, I just point out here. So if you are unsure, just check it. Okay, just check it. And then we will try to use this sigma, this Z transpose Z inverse times the Z transpose. So this term is given here. And the Z transpose we have already shown is a V times sigma transpose times U transpose. So therefore, once we times this term with this term, we will also have a cancel with the V first. Cancel with the V first. And then therefore it's corresponding to this element. So V times our diagonal part times the sigma transpose times U transpose. This term could be also calculate. We can also calculate. Just use this one times the search term, this one times the corresponding column one by one. Okay. So eventually that will result into this type of thing. So this is after we do the two diagonal matrix time together. So just because the Z transpose Z will provide the 1 over sigma square, and Z will only provide 1 sigma. So once we time them together, we still have a 1 verse sigma. So inverse of the sigma, inverse of sigma. So, and we use the U times our Y part. So just become U transpose Y, U transpose Y. And then eventually we can find the sigma square is the sigma inverse is still presented after we do the least square estimate. So it's equal to V, the orthogonal matrix, times the sigma 1 inverse times the corresponding U transpose Y element, and also the sigma R plus 1 inverse times the U transpose Y R plus 1 element. So the things just matches our statement. So once one sigma is small, the whole term will become the extremely large, which will result into beta hat is large. So this is our statement. That is how the small eigenvalue will lead into the large beta hat. So just because the small eigenvalue corresponding to the small singular value, so therefore corresponding to the large beta hat. Well, so we have already, so this is the issue about the least square estimate, And the next question we need to think about is, what is the case? So when the eigenvalue is small. So this give an answer. People, if you have ever heard about the ridge regression, the common keywords is a collinearity. So I use another color. The keywords is this, collinearity. Just stand for some kind of feature have the linear relation. Okay, so how we explain that? So just looks like we have a z, so which is our feature. So it may just have the several dimension, so like the 1, z1, z2, until the zr plus 1. So the collinearity just stand for there are some zi could be written down as very close to there are some matrix A. If I define z negative 1 as a 1, z1, zi minus 1, zi plus 1, zr plus 1. So just no zi here. Okay, no zi here. So if A equal to z negative 1. So this stands for the collinearity. One type of the feature, the ith feature could be presented as a linear combination of other feature. We call it as a collinearity. Okay, so what is the issue of that? So we know if this one is exactly equal, that will make your z transpose z definitely not invertible. But sometimes it's just a very close. Okay, some very close will just stand for the collinearity and making the eigenvalue small. So, but whether these things could be happens when we just implement our own data. So it's definitely could happen. So because once you collect your data, you just have the R plus 1 feature. We cannot use our eyes to detect, okay? So maybe some feature have strong correlation, but you don't know, you just keep them together. And you just apply the least square, you obtain a large value, and then you just make a conclusion. And everything here is you will just have, it's not just the correct stamp, okay? So first you need to try to detect that some collinearity. Just like the earlier example, okay? Again, earlier example. If you just definitely ignore, just like in this example, if you just directly ignore any kind of the cases, you will make a conclusion. X1 is negative to the Y. X1 is negative to the Y, but actually it should be positive. So we obtain the opposite solution. So therefore, this is the kind of the trouble from the collinearity. And in real data, it's definitely it could be happen just because I just give you a table of data, like here. We cannot use our eyes to identify. Okay, we cannot use our eyes to identify this collinearity is happen or not, because this is just stand for there exists some A, and this is maybe quite complicated, and we cannot use our eyes to find out. So therefore, sometimes I will suggest you first to try to consider the eigenvalue of the Z. Okay, trying to consider the eigenvalue of the Z, and then trying to see whether you can use if it's a small, it may just make you trouble if you apply the least square estimate. But actually, we should have a better solution. So this is a better solution called as a ridge estimate. Okay, so let's back a little bit. So we already know what is issue come from the least square. Just because the eigenvalue is small, will making the whole value is large, and that may sometimes give us a wrong solution. So can you just propose any good idea that can mitigate, just can solve this kind of issue. You can just think about for a while. Think about for a while. I'm not sure whether you have met this trouble. So when you do your own programming, so sometimes you need to write a function. So that is 1 over x. And once you use this 1 over x, there will give you some warning. Well, it may just divide it by 0, or divide it by 0. So therefore, sometimes to make your algorithm robust, you just adding a thresholding parameter. So commonly, like you write a 1 over x. So sometimes maybe your algorithm is complicated and sometimes your x could be close to 0. So that is the same issue come from here. The eigenvalue is small, making this value extremely large, and then the following calculation is all wrong. And then, so the very smart thing is that you just add a lambda here, okay? So lambda maybe like 0.01, so 1%. Okay, it's just sometimes we can treat this one as small things. Just for example, okay. So therefore, as long as x is positive, so no longer how small value could take, this one is still the 100, or it's still 100, cannot be extremely large. So just this number we call it as a threshold. So therefore, we can of course consider more large threshold like 0.1, but it may just change your value so much. So therefore, the idea is also same apply for the least square. Here we want to handle the sigma 1 inverse, and it may have the trouble. So why not just handle the sigma 1 plus lambda inverse? Okay, so it can guarantee this one will have the upper bound. It will not be extremely large, will not close to infinity. It will have an upper bound. So this is the idea of the ridge regression. Okay, just adding a lambda to that. And of course, we need to understand how the lambda is adding to this part. So usually, of course you can just use So the logic of ridge is just trying to solve this collinearity. But you can also just say, wow, it's just adding additional term to change your objective function. But it's not a good way to understanding. Okay, like this way. So a good way is that we should think about. So why we're adding this lambda square here? So we consider the same model, and then now our objective function is changed. So we no longer focus on the mean square error. We're also adding the lambda times the beta square. So usually we can write down our objective function or our loss function as a mean square, actually as a 1 over n times y minus z beta square. So this is how we solve the least square. If we're ignoring the second part, we ignore the second part, this one will corresponding to the least square estimate. But now we're adding a new lambda times the beta square. Then it will become a ridge. And this lambda is play a role as a thresholding parameter. So this lambda as a thresholding parameter. So here, of course, just like the example I mentioned, so once you want to handle the 1 over x plus the lambda, so lambda is sometimes you should tune by yourself, the hyperparameter. Of course, the small lambda just stand for it does not have any influence. Okay, small lambda just stand for does not have influence. Like a lambda is pretty close to 0. So these things will just almost the same as the least square. Of course, like here, if lambda is so small, it may not can meet our purpose. But if the lambda is large, it will also trouble. So it's just making the x, we just have a lot of kind of influence on our x. So therefore, lambda is something we should tune by ourselves. Which lambda we should choose? Well, so when lambda is 0, so it's same as the least square. When lambda is equal to infinity, so actually everything here will be directly thresholding to 0. So that will also have the trouble. Therefore, our ridge will also add a 0. Okay. So it's also easy to understand according to the objective function. So lambda we could also using as a trade-off, a balance between the first type of objective with the second type of objective. Okay, so if lambda is larger than for the second term, weight more, and then you just focus on second one. So whose answer must be 0. Okay, so that is the trouble. We lambda we should just twin by ourselves. But before that, let's just look at how lambda influence our reach. So it's a very kind of small idea that lambda here is just small is 0 is just correspond to this square, infinity equal to 0. But we should also know how the intermediate value of the lambda changes the value of the reach. Okay. Now, we first trying to find what is the value of the reach estimate. What is the value of the reach estimate? I think you probably know how to find the solution. At this moment, our objective is the argmax, it's argmin. So how we find is the argmin? So we just the same as the least square. So we notice that it's taking the derivative, taking the gradient for that. So we apply the gradient of beta. Wow, just a change. We will obtain 1 over n z transpose y minus z beta, adding the lambda times 2 beta. I just ignore the 2. Okay, so this is it's the negative part. So negative 2n, 2 over n times z transpose times y minus z beta, add the 2 times lambda times beta. So if you forget, let me just emphasize the trick. Okay, emphasize the trick. For the one dimension, so this is the one dimension. Okay, so y, z, beta, they are all constant. And then we're taking the gradient, take the derivative for the beta. So it's well equal to 2n y minus z beta and times negative z. Okay, times negative z. And adding the 2 lambda beta. Okay, so I just emphasize this trick a lot of time. So this one is n times r plus 1. This one, if we want to put it to the multi-dimension, this one is n times 1. Your resulting thing must be r plus 1. So you just change this one as a transpose. So therefore, it becomes this term adding this term. Okay, so this is how the gradient is come from. Just use this type of trick. And then we just want to make this guy equal to 0. So therefore, we just organize a little bit, okay? It's 2 lambda beta at 2 n z transpose z beta, adding the z transpose 1. Okay, so we can times the n for convenience and also just divide the 2. So it's a lambda n beta, adding the z transpose z. Equal to z transpose 1. So therefore, beta reach is equal to z transpose z, adding the lambda ni inverse z transpose 1. So this is how the reach gives the solution. Important thing is that compared with the least square, we have additional term, the lambda n times the identity matrix. One thing you should be guaranteed, one thing you should be convincing is that z transpose z, adding the lambda ni must have the inverse. As long as this lambda is positive. So this one must have the inverse. So just because the eigenvalue of this term stand for the eigenvalue of this term adding the lambda. So here, so therefore, all the eigenvalue come from here is non-zero. It's non-zero. Or is non-negative. Is non-negative. So it's either positive or zero. So and if you're adding a positive value, everybody will become the positive. So the answer we have shown before is that you probably heard that we have done when we handle with the range. So the Z transpose Z corresponding to the V matrix times the diagonal sigma 1 square to sigma r plus 1 square times V transpose. Okay, so this stands for every eigenvalue is taking a form as a square of something. Okay, so therefore it must be non-negative. Then so this one must exist as long as the lambda is positive. So we don't need to worry about the invertible version or not. Okay, so therefore you probably can get so how the eigenvalue play a role here, just because once we're using the Z transpose plus lambda ni, we can follow our earlier statement. It will become V times the diagonal sigma 1 square, adding the lambda n, and sigma r plus 1 square, adding the lambda n times the V transpose. Okay, just because we can directly breaking the I as a V times the lambda n times V transpose. Okay, so V times V transpose is a orthogonal matrix. They are orthogonal matrix, so they are can write them as this form. So eventually it's become here. Therefore, the Z transpose Z adding the lambda ni inverse will become V diagonal. Okay, become this part. So it's just a pretty good. We can know once sigma is small, we still have the lambda. So the whole term will not become extremely large just because we have the lambda. And eventually, once we want to use the Z transpose Z plus the lambda I inverse times the Z transpose Y. If you can still remember that kind of type of the calculation, so this term will become V part sigma 1 over sigma 1 square adding the lambda n times the U transpose Y, first element, until the sigma R plus 1. The R plus 1 element. Okay. So what is how it's come from? Okay, how it's come from? It's just we can just compare with the previous one. So this is the previous one. And now previous this sigma 1 inverse just come from we use the sigma 1 square times the sigma 1. So presented to the sigma 1 inverse. But now it's lambda n adding here. So therefore, it's become sigma 1 over lambda n plus sigma 1 square. Okay, so it's not necessary to require you to calculate the whole step, just need to understand how the lambda n eventually influence the result. So it's just a change the sigma 1 inverse to this type, sigma 1 over lambda n plus sigma 1 squared. So therefore, sigma 1 is small, it's okay. Course thing will become 0, okay? So as it's not becomes infinity, it's become 0. So this is something, this is such a kind of rich estimate. And of course, I also show you, I didn't present it in this slide, but I also didn't, I also show you how the final outcome will looks like. So this is the rich part. So the sigma small is okay. Sigma small is okay. And now we have already know what is the ridge estimate. So it's here. And we also use the LS to stand for the least square estimate. And a key kind of problem is still happens is that which one will be better. So even though we have mentioned one case that the least that the sigma, the singular value is more, the least square estimate is worse, but we still have confused about, have a question that how about in most of general case? So which one is better? So in the general case, you can answer me the question under some criteria. This one is better, just like the Markov theory, Gauss Markov theory mentioned. So this one have the smallest variance under our good estimator we have defined before. So the good estimator is trying to see unbiased, okay, unbiased. And the second thing stands for smallest variance. So this is our earlier criteria. Of course, if based on, also we use this criteria, ridge cannot be better than least square, cannot be better than least square. So here we will consider another criteria, so which called as a mean square error, mean square error. So that is to compute. So given the beta hat and the beta, so this is our target. So I just use a star for convenient. We compute what is the difference between them, the square difference between them, and taking the expectation. So this is a different with our bias term. So bias term trying to see the difference, the expectation of our estimator is equal to the beta star or not. So least square is unbiased. So this term is, when we adopt the least square, this one is 0. But for the mean square error, it's just stand for we taking the square of them and take the expectation. So these two things are not same, okay? And our next following theory, so it just told us what is the mean square error. So mean square error is equal to the square of the bias and adding the trace of the covariance matrix. The covariance matrix just we have mentioned at the beginning of this class is describe the relation among this n-dimension vector, and the trace just stand for their diagonal element. So variance of the beta 1 hat to the variance of the beta r plus 1 hat. So therefore, the mean square error consider the bias adding the variance. This part is the summation I from 1 to r plus 1 variance beta I hat. And this stand for the expectation and the beta star. Okay, so just for understanding about what is this. So this is the kind of things that we consider the bias and the variance together. So previous kind of criteria is to focus on, we first consider all unbiased, and then trying to choose one have the smallest variance. So that is corresponding to the case. We first making the first term is 0, and then trying to minimize the second term. So this is our earlier kind of criteria. But this criteria is just some old criteria. So 100 years ago criteria. Now, this one is more popular, okay? So why not just consider both of things together and trying to minimize this mean square error, okay? So previously, you're trying to use the Previous, we just trying to first making the first term equal to 0, and then minimize the second one. Now we're just adding them together, trying to minimize them together. Of course, if you minimize them together, you will have a smallest mean square error. So therefore, when we compare our ridge and the least square, we will adopting this kind of the criteria. So next week we will just focus on how to calculate the mean square error for the ridge and the least square error. So there are also some proof for that. I just skip and you can just take a look. So we will not follow the detail. So we just stop here.